Welcome to my computer science IA. The main purpose of my IA is to create an algorithm that can detect cigarettes from a live video feed. So what I have right here is an OpenCV implementation that I've coded up that actually takes a live video feed, or pre-recorded in this case, and separates out segments of the image using a simple threshold and then detection of what the ratio of perimeter to area of the shape that's being detected is, in order to generate region proposals for where there might be a cigarette. But this is just a starting point. So as you can see, each green bounding box is the edge of a particular region that the algorithm has considered probable to have a cigarette in it based on the parameters that I have supplied manually. Right now in the field of computer science, one of the most well-known ways to accurately be able to detect a certain object within an image is through something called a neural network. There are a billion different types of them, each one with its own parameters and specifications, but in my case, I'm trying to create a dataset that can work with a convolutional neural network, meaning it's specifically tailored to work with images in 2 dimensions. So what I have here are some basic pre-processing measures. So pre-processing means I'm going to take in these photos as input data, and for example, on image 1, I can create a bounding box around the cigarette and store the location of that bounding box in a file known as an XML file, which is a hierarchical format, in order to later retrace my steps, iterate through this XML file to gather these bounding box coordinates, and figure out what fundamentally differs between the regions that are labeled as a cigarette and the regions that are not labeled as a cigarette. Here I have 2 pre-processing programs. This one takes in photos from the loading dock, which is my colloquial term for the photos that have not been processed yet. It renames them, puts them into the photos, and it can double the image sets by flipping them horizontally because right now a computer can't tell the difference between the same photo that's been flipped horizontally or even vertically. So this is a great way to get more training data, so more data that can help influence my ability to make accurate predictions. The annotation script is very useful because it allows me to go in, create a bounding box around each cigarette that is then stored within the corresponding XML file for that image. So then later, once we get to the neural network part of it, we can unload that data and train a network off of it. So now we get into the actual neural network part of things. So my first step in this process is preparing the training images. As you just saw, I have a huge data set of cigarette images that have all been labeled with where exactly in the image the cigarette is. So if I go through this program, I can extract the boundaries from those annotation files and iterate over those for every single image in the database. So right now we have about 800. So it took 1 minute and 9 seconds to prepare the training data set, but as you can see, these are the labels. So 1 means that there is a cigarette present in whichever area it's referring to. It maps up to a different matrix. And 0 means that there is not a cigarette at that location. So as you can see, we have a pretty even random split. So here I'm just showing a couple of examples of the training data we have. So the label is over here on the x-axis, and all of the images have been normalized into a 128 by 128 pixel square. That is useful so that we can make sure we're comparing like-sized matrices to each other. So the next step is to build a convolutional neural network model. So here I'm using the TensorFlow model sequential. I'm starting with a convolutional 2-dimensional layer, max pooling convolutional 2-dimensional again, flattening it, and ultimately giving it 2 choices for an output, either 0 or 1. As you can see, it outputs this model architecture summary, in which it tells you a little bit about the number of parameters that are going into each requirement. The epochs are the number of times the entire network runs, and so as you can see, as time increases, loss decreases significantly and accuracy increases significantly, which is exactly what you want to see. We get a test accuracy by the end of about 85.7%, which is decently high. I did an 80-20 train test split for this set. So I used 80% of my data as training images and 20% as testing images. I found 80-20 split to be a pretty good, accurate measurement of how well the model is doing. So here I've created something that can save the model so that it can be rerun later without having to go through all these steps again. So now we get to the point of the product where this is what my client will actually be using. So what I have here is what I'm referring to as a test image. So this is an image, say you go out to a park, you're doing a litter pickup, and you photograph the ground like this. You have a cigarette. You want to figure out how you can teach a machine to identify that before you even look at the picture. So what I've done is, using that same pass filter that I described at the very beginning to determine region proposals, we have all these different region proposals, and as you can see, this is the one with the cigarette in it. So we're going to load the model weights back, and we're going to go through each of the regions and run it through that network to see what the output is. If the output is 1, that means it thinks there's a cigarette there, and if the output's 0, it thinks there is no cigarette there. And so if we run it on this new image, we get another model summary output, and here are the predicted values for each of the images. So I've set it so that these are the individual region proposals that I've generated, and for each one that it predicts 1, which is only the actual cigarette in this case, it's going to draw the bounding box around where approximately it thinks the cigarette is based on that initial threshold. So I would say this is decently accurate. Of course, training on a larger data set would improve it, and creating a UI that makes it a little more user-friendly would also improve it. For the sake of scientific research and data collection,